Imagine a blank canvas, just static. Now, what if I told you we could train a machine to turn that pure static into a photorealistic image, like a cat or a landscape?
That sounds like magic. We're not talking about image manipulation, but generating something entirely new and coherent from absolute randomness? How is that even possible?
It's not magic, it's a specific class of generative models. This paper, Denoising Diffusion Probabilistic Models, shows how to achieve just that.
Okay, so the name tells me a lot. Denoising means removing noise. Probabilistic models suggests they're dealing with likelihoods, but diffusion is where I got lost.
The diffusion part is key. These models are designed to understand the underlying statistical structure of data by observing how information gradually disappears. It's about a two-step process. First, we gradually add noise, then we learn to reverse it.
So it's like learning to undo a natural process. If a cup of hot coffee gradually cools, it diffuses heat. Can you undiffuse it to make it hot again?
That's a great analogy for the inspiration. On a practical level, this method yielded impressive results. On the unconditional CFAR10 dataset, we obtain an inception score of 9.46 and a state-of-the-art FID score of 3.17. For context, FID scores measure the distance between real and generated images. Lower is better, and 3.17 was remarkably low, indicating extremely realistic generated images for its time.
Those are strong metrics. So the promise is generating images that are both high quality and diverse, similar to what GANs achieve, but through a different mechanism?
Precisely. The common pitfall is thinking it's just about blurring and unblurring. It's deeper because it's a class of latent variable models, meaning it's not just reversing pixels, but truly understanding the hidden structural factors that generate the data. This allows it to create new data, not just reconstruct.
I see. So it's not merely reconstructing, it's understanding the data's fundamental structure, which allows for novel generation, not just reproductions.
Exactly. Now, to truly understand how it achieves this, we need to break down the two core processes: how we add noise in a controlled way, and then how a neural network learns to reverse it.
All right, let's step through the intuition. Where do we begin with this diffusion?
Think of it like this. Take a perfect photo and gradually sprinkle more and more digital static onto it, little by little, until it's just TV snow. That's the forward process.
Okay, so like a photo degrading over time, and then the model learns to gradually denoise data starting from pure noise to recover the original?
Exactly. The first part, the fixed or predefined forward diffusion process, is simple. We start with an image, then add Gaussian noise in small, controlled steps over many time steps.
So we precisely define how the image gets degraded. It's not random degradation, but a structured process?
Yes, it gradually adds Gaussian noise to an image until you end up with pure noise. Each step has a tiny bit of noise added, following a variance schedule. By the end, the original image is completely obscured.
And the key here is Gaussian noise? Does that make the math simpler, or is it specifically chosen for a reason?
Gaussian noise has convenient mathematical properties. For example, when you add Gaussian noise to an image, the result is still a Gaussian distribution, which makes the math for tracking and reversing the noise much simpler. Now, for the exciting part, a learned reverse denoising diffusion process. We train a neural network to do the opposite. Remove a tiny bit of noise at each step, starting from pure static.
So the network sees the static, predicts what small amount of noise to remove, and iteratively refines it until a clear image emerges? That's quite clever.
Indeed. Imagine starting with a heavily blurred image. The network learns to guess the original details, then applies that guess. It's like sharpening a very blurry photo, step by step.
But the network isn't just restoring a specific image, right? It's generating a new image. How does it know what image to converge on from pure noise?
That's a crucial point. We don't directly teach it the reverse process because we don't know. It's intractable. The network doesn't know the perfect unnoisy image directly.
So the analogy of unblurring a specific photo breaks here. It's not trying to find the original. It's learning the rules of unblurring to produce a plausible result.
Precisely. The network's job is to approximate, learn, this conditional probability distribution of what the image should look like after one step of denoising. It's learning the statistical structure of images.
So it learns to predict what a slightly less noisy image would look like, given a noisy one, based on all the images it's seen during training?
Exactly. Now, this brings us to the core technicality. How do we actually train this neural network to predict that conditional probability? What's the objective function?
Time to get into the details of how this denoising is actually quantified and learned. Show me the mechanism.
During training, we don't have to add noise step by step repeatedly. A direct consequence is that we can sample at any arbitrary noise level conditioned on the original image, because sums of Gaussians is also Gaussian, making the intermediate steps mathematically predictable.
That's a huge efficiency gain. So instead of running the forward process 1,000 times, I can just jump to any noisy state instantly.
Yes, it's a nice property. We can sample Gaussian noise and scale it appropriately and add it to the original image to get the noisy version at any time step. This means we can train on random noise levels.
Okay, so the network sees an image, say 50% noisy, and learns how to take a step back from that specific level of noise. It's not always learning from a slightly less noisy version.
That's where the reparameterization comes in. Instead of directly predicting the denoised image, which can be unstable, the authors opted to reparameterize the mean to make the neural network predict the added noise.
Wait, so the neural network isn't trying to reconstruct the image, it's trying to predict the noise that was added to it?
Exactly. This means that our neural network becomes a noise predictor. Given a noisy image and a time step, it outputs its best guess of the noise that was originally added to produce that noisy image.
That's a subtle but powerful shift. It seems easier to predict the component that was added than to guess the clean image directly.
And it makes the training objective remarkably straightforward. The network is optimized using a simple mean squared error, or MSE, between the true and the predicted Gaussian noise.
So, we add a known amount of noise, show the noisy image to the network, ask it to predict the noise, and then compare its prediction to the noise we actually added. Simple, elegant loss function.
Once the network predicts this noise, we then use that prediction to actually remove it. The mean can be computed as follows: from the current noisy image and the network's predicted noise, effectively giving us the next, slightly less noisy image in our reverse process.
So the network's output isn't the clean image directly, but the precise information needed to calculate the cleaner image at each step.
For the network architecture, the DDPM authors used a UNet. This model first downsamples the input, reducing its spatial resolution while increasing its feature depth.
Like an encoder extracting higher level features, but then UNet implies it needs to go back up, right?
Correct, after which upsampling is performed. A key feature is the residual connections between the encoder and decoder. These skip connections help preserve fine details lost during downsampling and improve gradient flow.
So it's like a sophisticated autoencoder that compresses the image into a rich representation and then decompresses it, but specifically tailored to handle the noise prediction task.
You've got the core mechanism. We now know how to train a model to denoise an image, but there's a big problem. These pixel space operations are incredibly slow and resource-intensive for high-resolution images.
The scaling challenge. So while it works in theory, applying it to large, detailed images is computationally prohibitive. How did researchers solve that?
That's exactly where latent diffusion models, or LDMs, come in. Instead of operating on raw pixels, they introduce a latent diffusion model, or LDM, which works with a much more compact representation.
So shrinking the problem space, like converting a high-res image into a smaller, more manageable data type before diffusing?
Precisely. The trick is perceptual compression. An LDM employs a cascaded approach by first training an autoencoder specifically designed to compress high-dimensional image data into a lower-dimensional latent space.
An autoencoder. So it learns to encode the image into a smaller vector and then decode it back into an image, ensuring the latent space holds all the important visual information.
Exactly. Once we have this robust autoencoder, the entire diffusion process, adding noise, training the UNet to predict noise, happens in this much smaller latent space. This allows to significantly reduce computational costs.
Aha! So the UNet is still doing its job, but it's processing much smaller data, which is way faster and uses less memory.
But if you compress an image, don't you lose details? How do you ensure the high-resolution output is still realistic?
That's the perceptual compression part. The autoencoder is trained not just for pixel accuracy, but to preserve the essential visual information, making the latent space perceptually equivalent to the original. The denoising in latent space maintains this, leading to perceptually equivalent to full-resolution images. So LDMs essentially take the powerful generative capabilities of DDPMs and make them practically viable for high-resolution image synthesis by moving the core diffusion operations from pixel space to a more efficient, semantically rich, latent space.
It's a brilliant engineering solution. Keep the core denoising idea, but apply it where it's computationally feasible, then upscale the results with a learned decoder. This must be why these models are so widely used today.
Indeed. From generating images from text prompts to image editing, LDMs have become a cornerstone of modern AI-powered creativity, showing how foundational theoretical advances can be made immensely more practical through clever architectural improvements.
It's incredible how far we've come from just denoising a noisy image. Thanks for walking me through the matrix, Arjun.